Oops. Okay. So if you remember y equals mx plus b, you remember that? It's the same thing.
It sounds like y could be
It's kind of
mx.
switched, right? It's really being written as b plus mx, but n is your slope. And b is your starting function. Your y-intercept, if you remember, is always the y-intercept. Anyway, it's the same thing. You just use different letters for whatever reason. I'm not sure why they did that, but he's trying to explain it in terms of p sub n, like where n represents weeks, 0 would represent 0, right? Our starting point, which graphically is where x is equal to 0 at the y-intercepts. Okay. So, you just putting your answer?
No,
Okay, where's 11?
only the what?
44 equals 14. I believe your sum has to have to be in there.
Yeah, he divided, he subtracted.
I think he's going to be sorry.
Oh, okay, yeah. So show us how you got, so you got 3 and then 4 n. How did, so you decided D was 4. How did you decide that?
It's the right.
Because to enable to get,
You're saying 240 would be.
I think here, this is where the problem is. It's 4 is our 4 weeks, so n is up. And then we're trying to find D.
Oh,
Right? So it's just a matter of you put the 4, because 4 is your number of weeks, D is going to be the slope. So just you can erase this by going to this.
So,
maybe you're trying to touch it.
And just tap on.
So
So you go
So we have to
D
solve
4.
if D is one.
Right, so we knew at 4 weeks we had
Oh,
47.
D.
I left you.
No.
Oh,
So do I have the right one?
Right.
or D, yeah.
4 is that
3 plus 4 times D, or D4 either way. But n is the 4 because it was P sub 1. Then divide both sides by 4, and that's how we got D. So 11. Good. So then we knew this right away. And then we also knew 4 gave us 47. So it's 2. And now D is the only thing left. Find by getting so then what is the explicit formula going forward to this? Because n will change depending on the number of weeks. So the formula will involve the piece of n. Yeah. This is the explicit. So in other words, we have, let me just write underneath here, we have piece of n equal to piece of O, which we found to be 3. This is what we needed. Plus D times n. These are the two we got to find. in order to come up with their formula. So we first put in 4 here and 47 here. And that left me with D, and then we found D to be 11, so now we have our specific. Now we can do them with E there. So we have to ask with the 2 variables that are left, P and N, what we're being given and what we need. So what does 289 represent? Is that a piece of N? Or is that our N? 289 is our population. P, and what we want to figure out is when, which should be weeks. So the N is the thing. Fine.
So it'd be 289.
11, and then -3. And
Once we have the formula, if we're given one of the variables, we can find the other. And it doesn't matter whether it's in population. You just have to solve for each other. Does it come out exactly to?
yeah.
Yeah. So, just to kind of summarize, perfect. Now you guys are getting nervous over there.
Yeah, we'll take it, man.
This is the general formula. You want to have this either implanted up here. A similar thing is y equals b plus mx, right? Where m and x, once you have the formula, you should have, depending on how you're writing it, an x and a y, or in this case, a b, or sorry, an n and a piece of n. Once we have the formula, d substitute it out, then we figure out if we should there. So the 2 things we have to find are this and this. These are the things. Sometimes it's given to us, sometimes we have to figure it out. Also recognizing what these represent, right? That this is where, like, in algebra, basically what this is, the variables usually represent something when it comes to a story problem. So over here, where we're talking about a population growth, this represents the population, this represents the number of weeks, this is the slope or the rate of change, and piece to go is our starting point. Questions on that? Yeah, so the 2 things we need are to start with what round up it's like we're solving round up and concepts. Go out put in like the 26.43. So from my understanding, this came out exactly. What if it doesn't? 26. If it doesn't, if it's a repeating decimal, then you have to round it. But if there's a decimal, just keep that decimal. Okay. Same thing with like persons. I had that problem. It's like how many people are part of this church, state or something. I mean, I got like 0.444, 0.43. Around this, that comes to like, does it matter? You know what I mean? If whenever you round, that's a great question. In terms of rounding, you want to keep it exact. You want to keep it exact as far as he's asked about rounding. Like we divided these 2, because a lot of times when we divide, we don't get exact. If you get a decimal that has a terminal number of places, don't round it. Unless the computer asks you to. But if it's like a continuing decimal that repeats and stuff like that, just take it out maybe 1 or 2 spots. Okay. Yeah. So the idea before I pull you guys up here, but the idea with the linear is that with our input, which here in a piece of it, that this is an additive pattern. If it's linear, then it's additive. And we see that additive pattern with this multiplication. Because if we add the same number multiple times, another way to do that is through multiplication, right? So like, for example, 3 plus 3 plus 3 plus 3, that's 12. It's the same as 3 multiplied by the number of 3's that I have, 4. 3 times 4 is 12. So multiplication is just a quicker way of doing multiple additions of the same thing. So in this case, we started off with 0 and 3. So 0 weeks, we started with 3. And then our change was 11. That means we're adding 11 every 1, 14, 2, 5, 3, 36, 4, there was 47. So there was an addition. And so the way we can arrive at figuring out what is it that we're adding, is to go, okay, this is what we're getting, this is what. So if I subtract 47 from 3, so the population outcome divided by the number of weeks, so 4 minus 0, we do the 44 divided by 4, which was 11. Notice you could do that with any one of these time periods. So like instead of 47 minus 3, I could go, let's just do these two time periods. 47 minus 36 minus 3. That's 11 over 1. 47 minus 25. Over 4 minus 2. 2, 2, going from one time period, or you can go 36 minus 14. 13 minus 1. 22 over 2. Subtracting is kind of the opposite of adding, right? So we're kind of just moving backwards. You can see that most clearly, obviously, 1. Any one of these minus the previous one is going to be 11. That's what the difference was. So it doesn't have to be this to figure out what the difference is, right? We don't have to know this necessarily to get the difference. Second one, or we got it. All right, number 2.
Explain as a
Yeah, I mean, you would.
So, they're supposed to 4 and 3 p.m. Input the information that we have up here. So we can PM, people, but to simplify that, to the average, it makes it a lot easier. 3, especially when things work, I know this there. 1 plus the ratio, or 3, yeah, which this is just
So when you put in the plus, when typing out the formula, it
Yeah.
didn't like that.
I didn't like it at all.
Oh.
And so I was just like, okay, so I was like, I'm pretty sure this is right. And then I was like, why don't you just like, just do those 1.4?
Yeah.
And then it was like, you're good. And I was so
Hmm.
fine. So this is your answer for the explicit form for this. For to find 12, you know that's 12. This is like 12. So you see 12. And the end is also here. So do the parentheses first because you end up getting there was other decimals after that, but I just like cut it off there because I was
Oh, I see. So you took, okay, good.
Yeah, because I was like the one after this one, I think it was like a 3 or 2 or 1, something like
Mhm.
that. So I was just like. You end up getting
You can put all of that into your calculator all at once. 14 times blank to the
12.
12th power.
Yeah, we should use the parentheses.
Yes. Yeah. Good. Excellent. What type of? So where the linear growth was additive in nature, the multiplicative or the exponential is multiplicative, meaning instead of our growth being added each increase, we're actually multiplying each increase. And multiple multiplications give us powers. Like 3 multiplied by itself 4 times, you can write as 3 to the 4th power, right? Whereas when we're adding it, the quicker way of doing that is going 3 times itself or added to itself 4 times. So we're starting at 14. 0 minus 14. And what we're doing every time is we're multiplying by 14 times 1.4. Does that give us 14 times 1.4? Should probably get mine out.
That's interesting.
6. And then the second week, we would multiply it by 4. So this is a multiplicative relationship instead of additive. Times 1.4 again. Right, this is 27.4. And we would continue doing that. And that's, you know, all of the explanations they're giving you. That's what they're trying to do. Let's see. Make sure. If you kept doing this, by the time you get to 12, you would have that 703. So this is a multiplicative relationship that we're describing. That's what gives us. The 2 main things we need to know is what is the rate of growth, R, and then what's our starting point. So on both of those, we need to know consistent. starting point. And then for the linear, we need to know D. For exponential, we need. Sometimes that's given to us. That makes sense. You can see that we start to get bigger totals a lot faster when we multiply. Right? Multiplication is a more powerful sort of increaser than additions. Why? Because, well, if I added 1.4 to 14, I would only have 15.4. Here I ended up with 19. And then it starts getting bigger as it goes, right? Multiplication is more powerful, so and we're continuing to multiply. Whereas with addition, it just goes up the same amount. And so graphically, what we see with this is that as time goes on, we get a faster and faster and higher outcome. Whereas with the linear, it's just steady. And so overlapping the two, if you have the same starting point, here would be my linear, here would be my exponential. And so the further out you go, the higher and higher this one will be. Whereas the linear will just stay pretty, steady and what have you. Okay, so the last one is it's different because it's actually not an explicit formula, but a recursive formula. The recursive is just if we were doing this one by one. So we have to know what the previous one is in order to get the current one. And then they threw in, where is it? There it is. So this is our logistic, which in terms of growth, like population growth tends to be exponential. Most of the time, if you're dealing with the population thing, it's exponential. It's compounding, in other words, and money, earning interest rates and things like that. All those things are exponential in their behavior. And so we try to model that. But when you talk about populations, a lot of times they have it can't continue like in the real world, there's limits. The pond is only so big. The earth is only so large, right? So you can't just continue to fill up more and more fish in a limited pond. And so that's what this tries to take into account. And so this is an explicit. Notice that we have the piece of n. We don't use piece of o. We didn't use, we can't use just what it started at 12 weeks ago. We have to use what it was on the previous time period. That's why you have the n-1 in here. N-1 is just what's the last week or whatever the growth rate is here. I think this is per year. So instead of piece of O, we put in piece of n-1. So we can't know the current unless I know the previous. It's going one time period by one time period. But it does involve R, the rate of growth. And then it has K, which is this is our carrying capacity. So this 1,200 fish, the pond really can only sustain 1,200 fish. All right, but we're going to do 300 and then one season and then season two. Yeah, well, I guess. I'm not really sure what it says 1.9% per year, so I'm assuming yes, it's a year. We have to go by what the growth rate is giving us too. So, what was I going to say there? So, no, you're great. So if I said after 12 seasons for part 2, you would have to find each one all the way to 12, right? Because you need to know what the previous year's amount was. That's why we only did 1 and then 2. This type of formula is not explicit. We can't just plug in the year or the season or the week or what have you. and find the answer, we would have to work it out at the table. And that's the recursive form. It's recursive. Think of re as like the previous, like trying to think of a word involving re that kind of gives that an example, but I'll think of something there. Record was the first thing, but that doesn't make any sense. Okay, so after one season, so I want to know P sub 1. We say P sub 1 as like subscript. And I think that's why he chose to do this, because it does help us see that recursive pattern. So then I need to know what the P sub O was. Well, because 1 minus 1 is 0. Right? So my starting point in season 0, I guess, is 300. And I'm going to add to that the rate of growth, which in this case is 190% per year. So what is R? Yes. Got to change this over to its decimal equivalent. So 1.9 times 300 over 1200. So this kind of gives you the percent that we're at in terms, or not the percent, but the fraction we're at in terms of the population capacity. So like 3 divided by 12, that's there if we reduce that, that would be 1/4. So we're at 1/4 of the carrying capacity multiplied by 300. So in other words, we're multiplying, even though they have them on opposite things, opposite sides there, the growth rate times the previous population, and then times the fraction of the carrying capacity that we're at. We're at 1/4 of the limit that we can go to. All right, so after season 1, what does that become if we do that? What do we get? $442.5. Great. Once we have that, so after, at 0, our starting point, we were at 300. Now after one season, we're at 442.5. And now we need to know season 2. Since we have this is our new n minus 1. Because for season 2, I need to know the piece of 2 minus 1, which is the piece of 1, which is this.
How did you get 2.5?
Because somebody said it. You guys getting something different?
Like in the equation, it's en minus 1 plus r in parentheses 1 minus over k and then in parentheses.
Oh, I wrote it down on that.
Yeah, because my original answer was 7.
Oh, you're right. You're right. I wrote this down wrong. So let me fix that. Thank you. Let me give myself some more room here. Okay, so it's piece of n times 1 minus piece of n minus 1 over k. Okay, so that actually is 3/4, right? Because this becomes 1/4, in our case, 300 over 1200. We subtract that from 1, that leaves me with 3/4. So that's going to give us a much larger population here. Yeah.
So the r was never supposed to be there?
Hmm?
The r was never supposed to be there.
Oh, oh, it is R. I had it there though. Right? Yeah,
At first, yeah.
Okay, I'm gonna need more room. P sub n equals P sub n minus 1 plus R. So this is what we're adding to, the previous year. So this would be 1 minus, we had 300 over 1200 times 300. So this actually becomes 1.9 times 3/4 times 300. You can put all this stuff into your calculator. You just need to use parentheses for sure, especially when you have an addition or subtraction in there. Plus 300. So that will give us something much higher. How much should we get for that? Tons higher, but definitely higher. Don't assume it's not me. It's what I gave you there that came out to 400. So 727.5. Okay. So good. So at 0, we're at 300. At 1, we're at 727.5. And keep that decimal there. I know that populations can't be a half a fish or whatever. But we want to use that in our next, though you're usually going to round your final answer there. So now this is my P sub 1. Right? So this becomes my new P sub n minus 1. We're going to go 1.9 times 1 minus, now we have 725 or 7.5 over 1200. This will make sure that we don't surpass or go too far over the maximum carrying capacity. That's a lot of numbers to put in your calculator. You want to break it down into smallers. Do that part first and then add 725.5 to that. Did you guys get something slightly over 1200? 1271.76, or you could say 0.8.
So the book says to round to 3, but if it doesn't say it like in the homework, you want us to put the whole.
Well, I mean, your homework is in WAMAP, but what you want to avoid is like if you're like putting something back into a formula, best to leave it in its original, because then when you round and then do a calculation on that rounding, it starts to the error that you might get begins to compound. So in the formula, I like to keep it as close to the actual number to avoid that problem. That's just a general good rule. But this you would have probably reported as 1272, right? If you're rounding it. Notice how that's slightly over the carrying capacity. So if we were going to do this another time, we're going to have to actually see some decline in our population. And we actually see that in this right here. If I have 1272 over 1200, 1 minus that is going to give me something negative. So now I have this sort of negative growth rate that's taking place. So we'd actually see a slight decline after that. So it kind of bounces around that carrying capacity. Because once you have a negative here, when you multiply, you're going to be adding a negative basically. And so it'll be a slight decline on the next season.
Wait, how do you get 12? I got 15.
Unless I put this in wrong. 1 minus. I don't know. This is what I got. You guys got something different? $720. Let me see what you did.
Oh, a regular. Okay.
See, 1 minus, you can't. You're subtracting this from. You do it the opposite direction.
Wait, so you have to subtract the 1 from here?
I would think. I don't know.
So, that's it. No, it doesn't work.
Yeah.
Normally, it would be.
Oh, yeah, that's one more.
What was that? This.
Yeah, yeah. So that you try to fit by this.
But you had to subtract it.
Yeah.
Oh, yeah.
I'm gonna go.
I'm more worried about the ratio.
There.
Maybe portions of it. How many kilometers are in?
So graphically, this kind of does a growth that kind of looks like this, and then it tops out and kind of goes like this. It's a very weird graph. This is not a typical equation that we would deal with, and it's regressive. And so if we're modeling it, it kind of becomes this logarithmic function, which somewhat logarithmic. Logarithms go like this, but this is not something that can be modeled that way, which is why we only have the recursive formula for the logistic thing. Okay, good. Where are we at on time?
The grass, it'll be asked at some point.
No, I'm just trying to give you kind of a visual.
It was about two.
Like you want to know what's the differences between linear versus exponential, right? Graphically, we can see how exponential gets a lot bigger, a lot faster. But for a while, what's interesting, and what we want to do is you'll be looking at for your written assignment, graphs that are not perfectly linear and not perfectly exponential. Most of the time, that's the case. Most patterns are not exactly one or the other. So, and in fact, here's an exponential. But if I were to only take a look like from here to here, you could, blowing that up, it would almost look linear in a way, right? So it's hard to spot that. Know that it takes a while for these to really appear exponential. It's not till we get to the later ends of these that we really see that taking off point. So there's a lot of similarities a lot of times between linear and exponential on a short period of time. But then there is a point where it's very obvious that we have an exponential versus a linear, because the linear is just kind of a straight line. But if it's just slowly increasing, that's kind of what happens at the beginning. If we hone in too close on a small period of time, it's hard to see that it's exponential in nature. All right. Any other questions on any one of those we did? Ready to go to the homework? Or
Are you?
I'm ready.
Just on number 2, I would be interested in how you define the rate. I just want to make sure.
Well, the rate on number 2 was given.
Well, if it wasn't.
Yeah.
Yeah.
Let's go to maybe a homework example where it's not. So I'm gonna exit out of here, stop share. Go back to here. Oh, okey. So going to the exercises. Any ones of these you would like me to look at?
Let's start with number 1.
Let's start with number 1. Are you just picking them?
No.
You can go through it, go through it.
Well, on your rate, there's the algebra rate, right?
Do they all give a rate? I'm not. See.
They all give a rate.
I think so.
Uh-huh.
Can you do number 2, please?
Number 2.
Yeah.
I think we avoid having you find the rate for most of these, but I say that because I'm just trying to go off my memory. Because a lot of times we need what's the word? We need logarithms to sometimes find that. Okay, so population of beetles are growing in a linear growth model. Here's my initial. After 10 weeks, here's what we have. Let's see. So piece of O is 4. Piece of 10 is 94. Okay, and this is linear, which the linear formula is Okay, so here we're told it's linear. 2 points they give us, so they're basically giving us this point and then this point, right? So here would be 0, time equal to 0, y value of 4. And here we're saying after 10 weeks, it's at 94. So basically find the line. This is time equal to 0. This is time equal to 10. This is in weeks. Right? This is graphically what it would look like. And so we're trying to figure out what's the linear equation that captures these points. 94, yeah. So actually, sorry, yeah, no, that's right. So just graphically, because sometimes it helps to kind of see it graphically, we want to know how many weeks this was. So this is my change in X. And this is how far have I risen. This is my change in Y. D, slope, is the height that we go, so change in Y divided by the change in X.
It's just like.
Here I'm going back to just X and Y like on a graph. We can use different variables there, but basically we want to figure out what is this quotient,
94
the rise over run, how far we've gone up, how far we've gone time-wise. And the way we find the change is through subtraction. So I'm basically taking the two results that we have for our population, which was 94 and 4, and then we're dividing it by the change in time, which was 10 minus 0. So that's 90, 10, which is 9. And what that finds me is how much it changed per 1 unit of time. And all of these ratios would give you the same: 1 week, 2 weeks, 3 weeks. We have a different rise, we have a different run, but these are all similar triangles that would give me the same ratio. So this is my D. The two things we need: starting point times 0 plus D times N. So my starting point was 4. And then I'm going to add 9 times my weeks. And that would give me my P sub N. So there's the formula. We're always after the formula first, and then we'll do an example. For this problem, I need to go back to it. So the first thing is, what's the explicit formula? So we type this in. And I think you have to use N. And then after how many weeks will the population reach? So P sub N, this is what we're after, question mark. Do we get 166 beetles? So notice P sub N is basically given to us.
So 166 equals 4 plus 9.
It was 4 plus 9N.
And then subtract 4.
We're either going to be given this population, this is where it really helps to think about what do these mean, which, so P sub N is beetles after N weeks, and N is weeks. So now they're asking us for time. We need to find N, and we're given the population. So then we subtract 4 from both sides, right? That gives me 162 equals 9N. Then we divide both sides by 9, and that will give me the weeks.
Where'd you get 162?
It's given to us on part B of the problem. It says, how many weeks will it take to get, you might have a different number. Yeah, we all get different numbers. So it said after how many weeks do we get that? So we're gonna go 162 divided by n. Like, or 9, sorry. And we get 18. And if it was 18.2 or 18.3, I guess we're going into the 19th week. But this time it comes out exact. Do you guys ever get decimals with that answer? They set it up so that you get a nice round number.
Got it.
Okay. Mm-hmm. Should we pick an exponential one? Let's see. Mhm. This is a disease. Oops. Okay, so let's go back. So number 6. Diseases tend to spread according to exponential growth models. Like what we saw with, when we were watching those infection rates continue to climb, and then first it was kind of slow, but then they're like increasing a lot more every week. That's an exponential growth, and that's just how population growth works. And we're looking at spread of disease. The disease tends to spread according in the early days of AIDS, the growth factor was around 1.9. And I'm thinking that's every year. About 1,800 people, 1,800 people died of AIDS. If the trend had continued unchecked, how many people have died from AIDS in 2004? Well, not during this time period. Yeah, because here we're talking about the growth rate when it started. So had we not found some ways to mitigate that, they're just saying if there were no mitigation of that, how many people would have died by 2004? Okay. All right, so let me write these numbers down. So with these numbers, what do we do with this 1.8 or 1.9? What was the 1.9?
1.9 is great.
This is our rate.
It's the overall rate growth.
Yeah. Let's see, common ratio growth multiplier. So the growth rate was actually 90%. I'm guessing. Was our R. This was our growth multiplier. So we've already added the 1.
That is
The rate of growth was 0.9. Yeah, they see in the early days of AIDS, the growth factor. So the factor is, so this is a good thing to know. So you have rate of growth. And then if we go 1 plus R, that's our growth factor. Yeah, rate of growth and growth factor. The factor is we've already added 1 to it. So this is R plus 1 and upwards. Okay, and in 1983, about 1,800 people had died. If the trend had continued, they're saying 2004, that's what we want to find. So let's take a look at our formula here. Piece of n equals piece of O multiplied by 1 plus R to the n power. So we're going to use 1,800 as kind of our starting point. Yeah, because this is all we're given to kind of go off of. So we're saying, okay, let's just say we're starting at, so that is year 0 for us in a sense. This doesn't have to be literally the date that AIDS started spreading. We just have to pick a starting point. If we know the growth rate, we can build a formula off of that. So, if we're talking about 2004, well, so since this is our starting point, let's get the formula first. We're starting with 1800. Our factor is 1.9, so I'm just putting that in there. That's not our growth rate. Are you guys watching?
Yes.
And then we need to know n. So now we're going to use this formula here. We found our rate and our growth factor, and we have our starting point. So what is the n that we're using here?
2004 minus 1980.
Yeah, whatever we're using as our starting point, we need to figure out how many years is that. So we find their difference. We subtract. So 2004, 2004 minus 3, which is 21 years. Mhm. So let's see, 0 was 83. So we're going to find the piece of 21. That tells us my power. I'm going to raise it to.
And then we just put that in the calculator.
So with just exponential growth rate occurring, this would have been,
1 billion. 1.2 billion.
yeah,
Did you
Yeah,
get an
there's a
exponent
decimal there.
answer on your calculator?
Hmm?
Did you get an exponent answer on your calculator? And that's how you write it down?
this is what I got on my calculator. And then I put the commas in there because
Just the.
I look at that many numbers, I need to know. Is that in the millions? This is 1.almost 3 billion people.
Watching the video, dude got the answer on the calculator and he was like, oh yeah, that's 1 billion. I was like, how do you know?
I didn't.
I don't know. I can't count that. I'd have to look at it, count, going.
Yeah,
One, two, three, 1, 2, 3.
And then I have to like double check.
Yeah. So had this just been allowed to spread at this rate, this is how many people would have died 24 years later.
So if you put like a 2.9 in your calculator, what if you put 2.9 for the growth factor?
Then you would end up with a very different answer.
But it would still be the answer.
No, because the factor is r plus 1. And so 1.9, it's told as our growth multiplier or our growth factor. The r is actually 0.9. So this is a 90% growth rate per year.
But I mean, what if what if instead of it being 0.9, it's 1.9, your rate?
Then it's going to be a much bigger number after this amount of time.
That'd be 190%.
You wouldn't subtract 1 from it because that's the growth. Oh,
Yeah, and they say that, so the way they describe it is diseases tend to spread according to exponential growth. In the early days of AIDS, the growth factor, which is already after adding 1, is 1.9. They also said the common ratio of the growth multiplier. Because this is what we're multiplying by, right? We're multiplying this by that. So it's the growth multiplier.
But
Nope.
so, because this happened to me last night where I was doing the phone and it resulted in like the exponent.
But exponent number?
So like the calculator.
Oh, in scientific notation. Yeah. So sometimes your calculator may do this. When you do this, it may give you 1.2855, a bunch of things. And then E10. Everybody get that? This means, so E means this is in scientific notation. It's giving your answer in scientific notation. The number here tells you how many places to move that decimal. Yeah. So here we would go. Actually, this is 1.2. Did it give you 1.2?
2.
Same number that I have there, but 10? Or did it give you 0.1?
It was 2.948.
So you have a different number. Oh, okay. So yeah, you would move it 10 spots.
So from where the decimal is
This,
at.
for this problem, it would say 9. If you use these numbers, this 9. So that means you gotta go 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your number.
What about where it was first two?
So you can move that 9 places from one.
For some reason, mine didn't give it to me.
Well, I just assumed those numbers are zeros.
Well, you can't figure it out.
You had numbers there.
Oh, yeah.
If they weren't given, yeah, you would add a 0.
Okay.
And if you ever got this same thing, 1.2, e to the -9, or e minus 9, that means you would move it 9 spots to the left.
That's what he's talking about.
Yeah.
And so I try to
Get it out of that. Usually there's a mode. Looks like it's here.
Well, not really bad. Not good. Yeah. Oh, man. You got it.
Yeah, sure. We'll see, look, it says 11. So 9 with it 11, even if it's only nine numbers, the other 3 are zeros.
So let's think about this whole 1.9 thing. So when we have a growth rate of, we had 40%, right? 0.40. Notice that, why do we have to add 1?
Where did 0.4 come from?
Okay, so first off, everybody's following me?
I
I want these formulas to kind of make sense to you. So if we're having a growth rate of 40%, that was one of our
Oh, okay. I see what you're
opening problems, right? So R was equal to 0.40, which is 40%. That means it's growing by 40% each time, right? So if we started at 100 and it grew by 40%, how much would we have? So if this is 0, at 1, we would have 140, right? You guys with me?
I am.
So if we're growing at 40% and we're starting out at 100, so time equal to 0 is our starting point. After one time period, we should have 140 because 40% of 100 is 140. With me?
Yeah, that makes sense.
When I take 100 and I multiply it by 0.4, what do I actually get? 40.
So, oh, I see what you're
So if I
saying.
just multiply my initial starting point of 100 by 0.4, I end up with something less.
You have
this
to
is-
add it.
What is any number times 1?
It's
Times 1 is itself. So when we multiply it by one also one in terms of percent is 100%.
Adding the one is like adding it, but all at once.
So when I take 100 and I multiply it by 1 plus 0.4, I'm keeping my original amount of 100. And then on that, I'm adding to that 40%.
It's like instant runoff of it. Redoing.
And so we're taking the original amount I had, we're adding 40% to that. 1 plus 0.4 is 1.4, 100 plus 40 is my actual increase. It increased by 40%. So that plus 1 is keeping the amount I have and then adding a little more to it. So at 2, then we're going, 140 times what I have now, which is 140, and then adding 40% of 140 to that.
Yeah.
Which comes up to 196.
40. Oops. What is it? 196?
Yeah.
So the reason why we have that plus 1 added to R is because when we multiply it, we still want to keep what we started with, whatever this number is. That 1 there keeps what we have and then adds more to it. Generally, when we multiply by something less than 1, we get a smaller number. Anything more than 1, we get something bigger. That's kind of the breakdown of why we add this 1 to keeping what we have, and then we're adding 40% to it. Okay, got lost some of you there. That's okay.
No,
Any other questions you'd like me to?
that part of it already makes sense.
So that's why we have the 1 plus R in the formula,
Right.
right? Our rate of growth, we want to add this much. We have to add the 1 is basically 100%, or it's keeping what we have and it's putting more to it. Keeping that. Okie dokie. You guys will continue to practice some of these ideas here. I can stick around if you have more questions. But at this point, I'm gonna say we're done with this right here. See you guys on Thursday.